that. Okay, this is lecture number 28, and since I have this all over here, the topics for today, we don't have much time today, so I will be approximately covering this 4 or 5 topics, and the remaining one I will give as a recording later on. Since in the next lecture we will be talking about BLDC, so let's make this lecture a little connected with your BLDC. This is a 4-pole from the, actually you can call it 6/4 pole. So this is a 6/4 pole BLDC, and this 6/4 pole BLDC is an outrunner motor, and you can see there are 6 poles on the rotor over there, and there are 4 windings over here on the stator side, which is actually inside. And this is totally unconventional, because every time you have been studying machines, your stator had been on the outside and rotor has been inside. So this is a different machine over there. मैं आ रहा हूँ मैं इसी पे, just because they are here, so I am going to link this topic with that MMF, so that part. So this is a BLDC machine. The sensor can be placed somewhat here. So if I can place that sensor supposedly at this transition over here, so just maybe this is just that, come on. So I have this sensor over here, come on, yeah. So I have this sensor over here at this point, and this sensor is actually going to tell me, because I have placed this over here, because the pole is starting from this point. So when the pole is going to start, I am going to actually find out that which pole is in front of that pole. So I will be regarding this one supposedly as the first pole. I will be taking this one third pole, third over here, and fourth pole. I can go it in the clockwise direction also, but it's totally up to upon the designer. Now since this winding is going to have like 2 ends over here, 2 ends over here, 2 ends over here, and then 2 ends over here. So this means that 8 wires are actually going inside that controller, and because of this Hall effect sensor, you are actually going to make either a north pole or a south pole over here. So this means that you are going to actually make this north pole. So this means that since this north is actually going to attract this south pole, so this is going to move towards this side, and then afterwards when this sensor actually senses that the north has actually come here, then you will make this one as a south pole, and then subsequently your channels are going to change, or the poles are actually going to change. Now the problem in BLDC is not the design or something. The problem in BLDC is actually the problem of having exactly the north pole and south pole arranged at the exact center. So at this point, if this is the north pole, this is being repelled here, this is being attracted here. So we never want it. So, and if in this case, supposedly, if I had made the poles in such a way that this all was north pole, this was south pole, this was north pole, and this was south pole. 4 poles on the stator, 4 poles on the rotor, they will be cogging. I don't know how many of you are familiar with the cogging word. They are actually familiar with them. Cogging means that the stator and rotor, they both are locked together. They don't even move over there. So either they are moving or they are not even moving at a subsynchronous speed over there. So here in this case, you always in BLDC machine, you are always going to have that 6/4 part over there. Or it can be 8/4 also, but 8/4 means that it will be again a multiple. So it will be, yeah, you are actually making the poles in break over there. So this will be north, south, north, south, north, south. So this will be north, south, north, south over there, and similarly north, south. So in this way, when you are going to make this one as 8, in fact, ये मैंने 16 बना दी हैं. So over here, if this is going to be 8/4, it's still not going to be workable. Crawling hogi, this will be crawling. But again, in this machine, you can't say, this is very important for the DEM students, that this machine is not going to be having that asynchronous or subsynchronous, because the frequency with which you are going to actually energize this A, B, C phase which are inside it, that is actually going to decide that what is the speed of it. And which speed, that is going to be dependent upon the Hall effect sensor. So Hall effect sensor, which gives the south pole, north pole, whatever its signal it gives, that is actually going to decide on it that which pole is going to be created when over there. Secondly, the problem over here is it, since this is a permanent magnet DC machine. This is a permanent magnet DC machine because the rotor is made up of permanent magnet. Now here the problem is this over here. Can you people identify the flux path that this is going to have? What I mean by this, supposedly, let me make one page over here, additional. So I'm talking about if you have a DC machine, if you remember you had your DC machine. Let me just make a small DC machine. I could actually copy it from somewhere as well, because I made that one previously also. So this one was it was a 2-pole machine. I'm just making a 2-pole machine. So this one was your pole. This is stator at present. So I am going to have a rotor. Okay, so certainly this means that when I'm going to make this one is your rotor, this one is your stator. Okay? I'm talking about normal DC machine which you have done in your machines course and over here. What is the flux path in this machine? You are having a winding on this one pole and you have a winding over here which is being over here. So what means that supposedly this is the north pole, this is the south pole, the flux lines are actually going to come inside this rotor, pass through this rotor over here, and then from the south pole they are actually going to complete their path through this yoke. And if this portion yoke is not there, the flux path is not complete. Now apply the very same on this diagram, how your flux path is going to be complete. Why I'm talking about this flux path? Because here I'm actually trying to find out the MMF for the air gap or any other thing which is actually going to be subsequent. Ji. Supposingly if this is north, let me just call it supposingly, let me call this one as north, this one is south, this one is again south, this one is again north. So what will be the flux path over here? The flux is being produced by this north supposedly. Certainly this is north having a flux flowing out of it. So it has to go towards the south pole, assuming that I'm not talking about the north pole at present. From here, how it will return back? जी कहाँ से आएगा? जी anyone? यानी कि this is going to come from this north again and going to complete its path from this, because from the north flux lines are going to come in. So this air gap length LG is the main culprit in your BLDC machine. This is an outrunner motor. Agar yahi cheez, if this would have been an inner runner, this problem would have been smaller. It would still be there, but it will be smaller. Here, this path from this one over here with the flux lines which are actually flowing from over here, this path, and it can be other paths also. I'm not talking about that much in detail over here. So this south to north or this flux lines, because these flux lines, they have to complete their path from here to here, or from here to here and from here to here. This flux paths are going to have that. And since it's air, that length may be certainly not just a simple length, it's actually a curved length because the flux is going to take the least path over there, the least reluctance path. So this air gap is going to, or this length is going to be using the major portion of the MMF which you are producing. And what is that EMF? That is the current flowing over here multiplied N and I. So we all know from the Ampere's law, now for them people, since we have done this in the last class, you had your formula for Ampere's law that was equal to H dot LC equal to NI. We did this yesterday. And I told you, if you need to find out your ampere turns, this means you need to find out H and multiply it by the mean length. Now in this whole circuitry, how many MMFs are required? Or which means if I want to actually convert this one into its magnetic circuit, there will be some reluctance of this portion. Then it is going to have some reluctance portion of this portion, because here now the flux density is going to be varying. By varying, I mean that at this point the flux density will be different, and at this point it will be a little different because of the pole arc over there. So over here, and then the air gap which is coming in series, and then the magnetomotive force. Now here, now tell me over here, this pole is going to be producing MMF or consuming MMF? Any north or south pole, anything. कैसे? The production यहाँ से हो रही है आपके पास. This flux line has to reach over there. So when I'm going to actually include this south pole, it's actually a permanent magnet over there, a ceramic material which has been made in such a way that there are like 6 poles over there. So will this be shown as a positive H or a negative H? Think on it. I'm not going to answer it. Think on it. In next lecture, we will talk about it when we're designing this part. Then next part, this MMF over there, that is actually going to be the air gap. And here this will be H of G. And yesterday I told them, we had this talk over there, that since we know in the air gap, we know B is equal to mu naught H, mu r is equal to 1. And if I convert this one, this is going to be H equal to B divided by mu naught. And since mu naught is equal to 4 pi into 10 raised to power minus 7, so I can actually write this one as 800,000 into B. Okay, approximately. If you inverse it, it has approximately 79642 something. So this is approximately 800,000 B over there. Now the flux path then returns back to the North Pole. Now here again, what is the MMF? Is it going to add or subtract? That is again a path, then again the air gap, and then it has to actually flow inside it. So MMF, now why I need this MMF over here? Because I need to find out IM, the magnetizing current. And those, since you are here over here for the first time, we talked about this induction motor equivalent circuit. Now coming back to the induction motor circuit over there, this was your per phase voltage, this one was your R1, JX1, RC. This current which is flowing over here, I am interested in this current because this is the magnetizing current. This whole equivalent circuit has nothing to do, these are all the losses, these are losses, these are losses, these are losses, these are losses of actually mechanical power being converted. This one is also a loss because this is JX2. I am only interested in this one, and to find out this JXM, because this JXM is going to be equal to certainly 2 pi f into LM over there, and this LM is going to be equal to the जी किसके इक्वल होगा फार्मूला वाइज नॉट ये तो उल्टा n square by r. So I have the turns over here and the reluctance. Now this reluctance is only going to be of the air gap, or it is also including the other reluctances. They will be including out. So this is not just going to be RG, this is actually going to be the R total. Yes, certainly one thing very important, RG is going to be a significant portion of this R total. So we can assume it that RG is approximately equal to, this is not a very good assumption, but still we can go with that one. So this portion, when you have found out this LM, so you have to actually find out. Now finding out reluctance for structures like this, or maybe something like this where the shape is curved, it's very difficult. It's very difficult to find out, because we know what was the formula for reluctance. The formula for reluctance was you had the LC divided by mu naught mu r into AC, where LC was the mean length, mu naught was the permeability, mu r was the relative permeability, AC was the cross-sectional area. Here the cross-sectional area is not uniform. Here it is different, then it is different, then it is different, then it is different. So you will have to apply something, some rules or some Simpson rule. I'm not going to go in detail of this one today. We're going to talk on that one also. It's a mathematical rule where you actually take the 1/3 Simpson rule, SIM, not Simpson, that cartoons or whatever. This is Simpson, SIMPSONS. So here the problem here is this, that the armature, the area is variable. So instead of going with the reluctance formula, what we do, we all use the Ampere's law, where H dot LC is equal to NI. And if we can find out NI, this is MMF. If I can divide it by N, this will give me the current that is required. So here in this case, this will be IM. And what will be N over here in this case? This will be equal to, जी किसके इक्वल होगा? If it is stator, this will be equal to the per phase stator turns per phase over there multiplied by KWS. Very, very important, because the winding factor is very important. Winding factor, because all the windings in your stator, they are not having the same effect on the, so this is the winding factor. So you only need to find out from this formula. You have your KWS because you have designed your stator. You already know your TS. You don't have this value. This LC is the important thing over there, and this H. So now if you are talking about an induction machine, let me go towards some induction machine where I have actually made an induction machine. Let me just find out. Yes, okay. In this induction machine, you are applying A, B, C over there. This is the flux lines which are entering over there. So now the stator teeth, this is going to have 1 mmf. Stator core, this is going to have 1 mmf. This air gap, it's also going to have an mmf. Then the stator teeth, another mmf. the rotor teeth, the rotor core, another MMF. Sorry. So all of these are coming in series. And all this analysis will be done per pole. That is the same thing we did yesterday. So coming back to whatever we did yesterday, I'm going to now go towards my one over there. So the first thing over here is it that we need to find out H. And for H, there are two things. We need to find out H in 2 or 3 different quantities. One is the H in the air gap, which we'll call it Hg. Then we need to find out the H in the stator teeth over there, which we'll call it HTS. We need to find out also the core of the stator over here. And then we also need to find out the H in the rotor core and also the H in the state core slot or teeth. Actually, we will call it actually teeth over there. That will be easy. So this will be TR. T for teeth, R for rotor. T for teeth. So these 4 things, actually 5 things, you have to find it out. And when you have found out all these 5, you are going to multiply it by their mean length. अब वो mean length क्या होगी? That is actually a questionable thing over there, because here in this case, we know this length is going to be equal to this for the teeth. We know this length is going to be equal to for the air gap. If the teeth is there for the rotor, then this one is going to be the length of it. Then there is the rotor core over there. So every time you need to find out this length, you have to take into consideration the fringing effect and other effects which we are going to discuss today. So for first purpose, the first thing which we are going to do today is for the air gap. And last time, yesterday, what we did over there, these were some of the attributes which we have used openly up till now in your induction machine design. Just repeating them again. L is the length of the machine, Li is the net iron length, Lg is the air gap length, Ys is the slot pitch, and here this is one slot, so this is once, and this distance over here is equal to that Ys. Now, if I have made this one in circular form, I have made this one in the pure developed form on the paper. So this distance over here from this point to this point, certainly in terms of some units, millimeter, centimeter, this is your slot pitch. Then I have the slot width. So slot width is going to be equal to this distance over there. So that is your slot width. Then I have the teeth width over there. Now, I don't know how much design you have done previously up till now, but you have been told that if you are working on a small machine, this WT and this WS, you have been told that you can make them equal, or this ratio has to be something near about 2 to 3 or something like that. That depends upon the size of the machine. Then I have W0, that is actually the slot opening, and by slot opening I am referring to actually a slot which is going to have, let me just make a slot over here. So okay, come on. Usman is sleeping, that I can confirm. So this is, come on, why the pen is not working? Anyway. So this is my slot, and in this slot, this is a parallel slot. This opening is called as W0. Okay? And this over here, this distance to this distance is the depth of the, you can call it as the stator DSS, actually stator slot. So this is DSS over there. So, and if there are ventilating ducts, then I'm talking about the ND, and if they are ventilating ducts, they are going to have some width as well. So what we did over here, the flux, the case number 1, which we are discussing here today first, again I'm repeating it actually from the last lecture. This is the flux which confines in the teeth, and the case is this, that the slot are having no opening, which means that this is all iron over here, and only flux lines are flowing from one portion to the other. This can be the stator as well, this can be rotor as well, or opposite way. So this is just one case in which the flux lines have to go towards the iron. So I am assuming that all the flux confines inside this teeth area which I am identifying over there. So all the flux lines, they go inside this one, and then afterwards, when I have this case, I need to find out the H which is inside this air gap. And for that purpose, what I need to first of all find out phi s. Now what is phi s? This is the flux through slot pitch. What is slot pitch? Again, coming back, This is my slot pitch over here. So how much flux is flowing over there? And one assumption which I have done, that only yellow color lines are actually the flux which are flowing. The pink color ones are not happening in case 1. We will talk about them later on in case 2 or case 3. But at present, only yellow color ones are there. So this means that my length LG is same. It's not having any fringing effect. There is no increase in the length LG over there. So this means flux through the slot pitch, what was phi S? I told you yesterday also that whenever you are designing a machine, you already are given phi m. Phi m is the flux per pole. So when you want to find out phi s, this will be equal to phi m divided by number of slots per pole. So you have the total value over there, and I guess I have written this one over here as well. So if you want to find out phi s, this is equal to phi m divided by ss divided by p. And here the difference over here, phi s is the flux per teeth, which means from one slot pitch over there. Phi m is the flux per pole. So certainly this is a larger quantity over there as compared. Now to find out, first of all, I need to find out b over there. B will be equal to phi s divided by L dot ys. What is L? L is the length of the whole machine. Ys is the distance from this point to this point. So in this distance, this is Ys multiplied by L. That is actually the area of one slot pitch. So over here, what is the formula for phi? We know B dot A. So what I am trying to find out, I am trying to find out B over there. B is going to be equal to phi S divided by L dot Ys over here. किसका? नहीं, अभी हमने बात की है, this is case 1 where only yellow flux is flowing, pink color flux is not flowing. ये अंदर वाली है. This is this length which is exactly perpendicular to the two surface air gap. अभी हम fringing effect देखते हैं. In case 2 I will talk about this one. So this is your B over here. You have found out this one. Then the next thing, one thing very important, I told you yesterday also that chapter number 4, this article 4.5, instead of using this reluctance symbol, they are using SG. So don't use this one. This will actually confuse yourself. So I'm using this RG. So if you want to find out RG, this will be equal to LG. LG is still same, divided by mu naught, because there is no mu R, because this is just air. And then I have L dot Ys. What is L dot Ys? This is the area of one pole pitch. And since I know B is equal to mu naught H, H is equal to this 800,000 B. And now for that air gap, if you need to find out ampere turns for the air gap, you will multiply your H, which we have found out, by LG. So this means your ampere turns for the air gap will be found out by 800,000 multiplied by B multiplied by L of G. But for that B, you need to find out phi s. Phi s can be found out here, and this phi s will divided by L dot ys you have. So if your machine is equal to case 1, then you can find out your ampere turns. And why I'm doing this again, I'm going back to the diagram. I'm trying to find out the ampere turns here in this one, because air gap is the most disturbing thing, because here the flux lines can actually float straight as well. They can actually also have a fringing effect. This is case 1 where all the flux lines are confined in that same LG length over there. So this is case number 1. Case number 2 over here. क्या है? हाँ, one slot. This is one slot reluctance. ठीक है? Of course, लेकिन हम यहाँ reluctance से खेल नहीं रहे हैं. Again, I told you we are not finding out the reluctance of the whole system. What we are interested in, we are finding out ATG. हम करेंगे क्या at the end of the day? In fact, let me just go on the end over there. The end over here for this lecture today is this, that I will be having this one. What I will do, the total magnetizing MMF would be equal to ATG plus AT for the stator teeth, ATTR for the teeth of the rotor, ATCS for the the core of the stator, ATCR for the rotor of the core of the rotor. So when I will have all of this, this is going to be called as AT60. Why 60? I will tell you later on. ये 60 क्यों है? So using this AT60, you can find out IM. And why I'm doing this now, I will leave this one as a bonus question for you at the very end, that this IM is given as, now you have found out AT60. 8060 divided by KWS into TPH, as I told you, ठीक है? P multiply क्यों हो रहा है? Because this P is having, so this is the ampere turns for one pole, because we are every time doing the equation for one pole. So we are, but what is this 2.34? Try to find out this one. ठीक है? Try to find it out. ये खैर इस lecture के total end पे जब when we are actually, in fact, हैं? नहीं वो नहीं, बोनस देने का मूड है, डोंट वरी ऑन दैट पार्ट, आई हैव द मूड. No, it's not fringing factor. So now case 2. Let me just make this diagram. Achha, now I am not going to make the diagram every time like this. Over here, I'm going to make this diagram always like this. So I'm just going to copy this diagram. This is actually easy for me. So I'm just going to copy this diagram, and my case 2 is equal to something like this. Achha, now in case 2, what I'm going to do, I am not going to make let me just in fact delete all this. This is gone, and not this one. So this is gone, this is gone, and this is gone, and certainly this is gone. So now I have the slot opening as an open slot. So what I have now is an open slot over there. And here in this case, all the flux lines are confined again in the teeth. And for the distance over here, which I am actually talking about, this is my y of s. That is actually slot pitch. Don't worry on the small imperfections over there. And this distance over here is certainly equal to L of G. And what is this distance? Let me use the thicker one. This is equal to omega s, the width of the stator. Now, question over here. Here the flux lines are going to be, if the flux lines are confined in this over here, no issue. Why? Because now what is happening? Now the flux lines are confined in a distance which is smaller than Ys. This is smaller than Ys. So here this time when I'm going to find out B, so B would be equal to again phi s for slot pitch. This time this will be equal to L dot WT. This is very important. Previously what was happening? This was total core. So this was over here, total core over here, this was total core over there. So there was nothing effect over there. But here, flux will try to flow through this part. Again, I'm still not taking the fringing. In the next part, I will take the fringing effect. So this time, B is going to be equal to this phi s divided by L by T. And this one would be equal to phi s. This is just one change over there. You can call this one as Ys minus omega s. Oh, sorry, Ws, not omega. Okay, that's just simple taking out. And if you want to find out the reluctance of this one, the air gap, this one would be equal to again Lg. And this time, previously what was over there in your Lg, this was mu naught Lys. This time it's not going to be just Ys. This is going to be mu naught L and Ys minus Ws over there. Now, second part in this same case, now the flux lines, they don't confine in this one, which is actually the third diagram of this one. And now the flux lines, I'm going to make them over here by some other color. So now the flux lines, I have to make them curved a little. So this is your flux lines over here, like this. And now the flux lines are flowing still from the teeth, but they are taking a little bit large area. So now over here, what will happen? G, what will happen now? No, इस केस 2 ये भी अभी मैं केस 2 पे हूँ. केस 2 के अंदर ये एक सेकंड प्रोविजन है, क्योंकि एवरी टाइम वी नो फ्लक्स. प्रॉब्लम क्या है यहाँ पे? इस टीथ के अंदर इस पॉइंट पे फ्लक्स डेंसिटी ज़्यादा होगी. यहाँ से सारा फ्लक्स फ्लो कर रहा है, बिकॉज ऑल द फ्लक्स phi s has to flow over there. So depending upon the area of this one, whatever B we get, flux density will be more. And when flux density will be more, flux lines will try to also flow from here, because it's not just air over there. There are conductors over there, and conductor will be having some mu r. Okay? It's not just simple air, it is some conductor placed over there. Maybe they are circular conductors, or maybe they are bar conductors over there, or rectangular conductors, totally up to the designer, whoever has designed this one. So now in this case, what will be? So this time, your Ys, would be, if I can actually let me copy this diagram. I don't want to clutter it over here. So, क्या आया? अगेन सॉरी
0.85 into
नहीं देयर इज नो फैक्टर कमिंग अप. यहाँ पे एक और कोफिशिएंट आएगा, अभी मैं ऐड कर रहा हूँ उसको.
15%.
नहीं, ये तो आपने डिसाइड नहीं करना. ये तो आपके क्वेश्चन में आपने मशीन्स के कोर्स में मैग्नेटिक सर्किट्स में हम ये बताते हैं आपको कि देयर इज अ फ्रिंजिंग ऑफ 5% 10%. सो दैट इज डिपेंडेंट अगेन ऑन द परमिएबिलिटी डिफरेंस फ्रॉम वन मटेरियल टू अनदर. जिस तरह से ऑन द इंसिडेंस ऑफ लाइट व्हेन यू आर गोइंग फ्रॉम वन मीडियम टू द अदर देयर इज अ रिफ्रैक्शन एंगल और व्हाटएवर. द सेम थिंग हैपेंस इफ यू आर गोइंग फ्रॉम एयर टू, वो एयर आयोनाइज्ड है, उसकी मॉइस्चर कंटेंट क्या है, उसका टेम्परेचर क्या है, दैट डिसाइड्स ओवर देयर व्हाट इज दैट change over there. Now here anything important, this distance over there actually थोड़ी सी मैंने यहाँ पे एक छोटी सी गलती ये की है. Of course बिल्कुल होगी, that's going to be problem. इसीलिए they have done in the design that this distance and this distance they both have to be same for smaller or medium machines. That's why, क्योंकि अगर उसमें fringing 10% 20% है और आपने slot को पतला रखा हुआ है, then there will be an interference. So then again there will be chances of having a high flux density over there. अच्छा जी, now one thing I have actually done. So I'm just cutting off these two. And why I'm cutting off these two? Because the distance which I actually want to measure over here is this distance from this distance to this distance, and I'm going to call this distance as ys dash. So what this means, देखो, listen this very carefully. What I am doing, ys was the slot pitch from one slot center to the other slot center. In between it, wt was the teeth width. Now, in case number 2, this is a sub case of case number 2, where I am assuming that the flux lines, they are flowing a little away from it, but it's not equal to ys. Because if they equal to ys, then it's a wrong thing. Just for elaboration, I draw this three lines on the other side, but practically it will be just a small distance, and this distance is equal to ys. Now ys dash over there. Now this ys dash, in this case, this is very important. Now this ys dash is given as, over here, see this very carefully, is given as delta wt. Now what is this delta? This delta is a coefficient factor, but this coefficient factor is not used that much in your book over there. What they have done it over there, they are calling this ys dash equal to ys minus kc omega w naught. And what is this kc? Kc is called as the Carter's coefficient. You always remember the American presidents. And this kc is equal to w naught divided by lg over here, if I'm not wrong. Yes, this is one. And this one is called as the Carter coefficient over here. That here in this case, because this is an open slot, w naught is equal to ws. Same thing coming up over there, because slot shape can be anything. So slot shape can be anything. Now this Carter coefficient is not just going to be very simple. You are going to actually have a curve of this one, and Hamza, please add this curve from this book in the formula sheet over there. And over here on the y-axis, I have this Carter coefficient. I'm just writing Carter over there, coefficient word, you can write it. So this is ratio over here, and the ratio is actually, I'm not using the symbols over here, the variable. I'm taking it as slot opening divided by the gap length. Now, answer me on one thing. If the ratio of slot opening divided by gap length is larger, think on it. आपकी slot opening, go back on this case, यहाँ पे जिस तरह से आपकी slot opening ज़्यादा है, divided by, what is being divided over there? Gap length. So if this ratio, this supposedly x divided by this y, if this ratio is more, Carter coefficient is smaller. Carter coefficient is smaller. This means that this Kc is smaller. Ys dash will be having, not fringing, it will be having less. Smaller. It will be smaller. So ys dash will be approximately equal to ys. क्यों? क्योंकि आपका गैप लेंथ ज़्यादा है, ओपनिंग भी अगर ज़्यादा है. सो दिस वन आपके सामने है. फ्लक्स लाइंस यहाँ पर हैं. कहाँ पे जाना है उन्होंने फ्लक्स लाइंस ने? दे हैव टू रीच दिस पॉइंट. नाउ इफ दिस स्लॉट वाज समथिंग हैविंग एन ओपनिंग लाइक दिस, ना ओपनिंग कम है यहाँ पे जिस तरह से है, ओपनिंग कम होने की वजह से फ्लक्स लाइंस विल ट्राई टू फ्लो मोर थ्रू द टीथ ओवर देयर, बट इफ द ओपनिंग इज मोर, the flux lines will be more confined in the teeth only. So over here is more, so this means that W naught, which is the opening over there, so this Carter coefficient, so you are going to find out this ratio and you are going to plot this curve over here for the semi-enclosed slot. This is the semi-enclosed slot. Approximately, not exactly. In the book they have actually shown it a little slow over there. This is your open slot, and for example I'm just write down the turns over there. This is equal to 0.8, and then I have 0.6, then I have 0.4, then I have 0.2, and certainly then I have this 0 over there, and this ratio 2, 4, 6, 8, and then certainly 10, and then so on 12. So what you are going to do, you are going to find out this ratio, slot opening divided by gap length, go in this graph over there, find out wherever supposedly your ratio is 4, you have a semi-enclosed slot, this will give you the Carter coefficient, use that Carter coefficient of 0.5 or something in this one and find out ys dash. Now based on this ys dash over there, this ys dash is going to give us the total one. So what is going to be now? This is going to take a lot of time. So now over here I want to find out what? I need to find out B. Now B is going to be changed to B dash. ठीक है, क्योंकि आपके पास लेंथ चेंज हो चुकी है. So here B dash is going to be equal to फ्लक्स अभी भी उतना ही है फायर्स. अब एरिया कितना है? Previously what was? This was L dot ys. Yes, this is now ys dash, so this will change to L dot ys dash, and they have actually written this one as also, I'm writing down the other form. This is ys divided by L dot ys into ys divided by, this is again, we just opened it over there, so this is equal to y kcw naught over there. So this is going to be equal to B, and what is B over here? B is this portion over there, and let me draw this portion over there. This is B. So I have now B dot kg. Oh, come on. So this is kg. And what is kg over there? Kg is this form. Now what is this kg? अब ये kg एक नया कोफिशिएंट आ रहा है. ठीक है, अभी तक हमने मशीन डिज़ाइन में यहाँ पे इंडक्शन मशीन में ज़्यादा कोफिशिएंट्स नहीं आए थे, ट्रांसफार्मर में काफ़ी आए थे. सो टुडे नाउ आई हैव मोर कोफिशिएंट्स कमिंग अप. दिस इज kg. kg इज गोइंग टू बी कॉल्ड एज द गैप कॉन्ट्रैक्शन और एक्सपेंशन फैक्टर. उस्मान इज हाँ, ये भी सो रहा था. आई हैव सीन हिम. एक्सपेंशन फैक्टर. So this is the gap contraction factor or the expansion factor over there. So now using this B dash, we can find out now the ATG. This will be equal to here this time. Again, this will be 800,000 into B dash into L of G. बिल्कुल, contraction factor, that's all. So this one you can write it over there. Now one thing, this is based on the assumption that Lg is constant, but practically ऐसा नहीं है. Why? Because the flux lines, this flux lines, they are taking a little longer path over there. So here for the Lg you are going to have again a factor applied over there, and that factor will be coming up. So this is going to be actually the second part, assuming वो इसी वो kg के साथ लिंक्ड होगा, बिल्कुल सेम exactly. So assuming Lg is increasing due to fringing, so this is increasing due to fringing over here. So you have now Lg dash equal to k of g multiplied by Lg. So you have just gap contraction or expansion factor, and if you write down the whole formula over there, what is kg? This is actually ys divided by ys minus kc w naught into Lg.
फैक्टर कहाँ से है?
ये के जी यहाँ से है, इधर दिस वन
डैश की नाम पूरा दे दिया।
पूरा नाम दिया हमने, वाई एस डिवाइडेड बाई वाई एस माइनस वाई एस बाई वाई डैश, गैप कंट्रैक्शन फैक्टर। देखो ना आपके पास क्या हो रहा था, गैप क्या था, ये वाई एस था, ठीक है। अब आपके पास यहाँ वाई एस, सॉरी सेकंड डैश, वाई एस डैश आ गया। सो वाई एस डिवाइड बाई वाई एस डैश, देखो ना वाई एस दिस वन, वाई एस डैश दिस वन, सो वाई एस डिवाइडेड बाई वाई एस डैश, सो दिस फैक्टर डिवाइडेड बाई वाई एस डैश, एंड सर्टेनली दिस विल बी ऑन दी हायर साइड, मतलब क्योंकि वाई एस डैश छोटा है, सो इट विल बी ग्रेटर देन 1 over there. So this will be your LG dash, and now this time when you are going to again this time find out the MMF for air gap. So the MMF for the air gap is going to be again ATG equal to 800,000 again multiplied by B dash, then I have kg into L of g, because this is same over there. So now this is your so you have this one over here. Otherwise, if you are not having any increase in your LG, then you have some. किसका? नहीं नहीं, ये ऑफ कोर्स ये अभी तक आपके, अच्छा देखो, वन थिंग वेरी इंपॉर्टेंट, इफ यू गो बैक ओवर देयर, क्या इस तरह का कोई, कम ऑन, इस तरह का हमने अभी तक कहीं इंडक्शन मोटर में सर्किट देखा है अभी तक? नहीं। हमारे पास स्टेटर की साइड पर भी ओपन स्लॉट्स होंगी, रोटर की साइड पर भी ओपन स्लॉट्स होंगी, देन आई हैव द केस, एंड दैट केस इज एक्चुअली कमिंग अप इन केस नंबर 3 or 4. So let me just add that. I have now, let me just start from another one. This is case number 3. So I have now case number 3 over here, and